Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole.
And I'm Brian, and we're both from Calgary, Alberta, Canada. And this episode, if you were paying attention when you downloaded it, is episode 50. It is literally the episode number of how old I feel every day.
Brian's not quite 50 yet. I am so impressed with us that we have made it to 50. This is a huge deal. So exciting.
That's a lot of episodes for Nicole to have to put up with me.
Well, I mean, technically you've only been here since 27. But it is a lot of episodes. We started out with weekly episodes and then we went bi-weekly. So we've been doing this for roughly a year and a half, maybe a little bit longer. It's exciting. 50 is a huge milestone for me. This is really exciting. So thank you to everybody who's listening now and who's been listening to us hopefully for a while or maybe even since the beginning. We really, really appreciate your support. We also appreciate the support of our Patreon subscribers. Thank you for listening to our extra episodes.
For more or less than the cost of a Major League Baseball one, you can hear us talk about more interesting engineering failures. That's $5, and we have a dedicated RSS feed that gets you all of our regular and mini fail episodes in your favorite podcast app.
So just $5 a month and you get twice the content. Way more train tangents, which you know that we love.
Things go off the rails.
And you get to support our show.
This week in engineering news, improved solar electricity performance. Our current solar electricity panels are made from silicon, which is reliable, inexpensive, and the structure and performance are well understood, which are all great things. Unfortunately, though, silicon is only 20% efficient in converting sunlight to electricity, which is the whole purpose of a solar panel.
That's not very good. 20% is better than nothing, but 20% is not great. That number surprised me.
Yeah, and actually with a lot of some technology stuff, for engine-related things, we don't see much better than 20% efficiency. So there's a lot of inefficiencies in the conversion process of one form of energy to the other. So while the panel materials are inexpensive, production of the panels themselves can be really expensive and really complicated. So in an effort to lower technology costs, researchers have been exploring the potential of CadTel, which is a mixture of cadmium, selenium, and telluride, which is where the CadTel name comes from. And currently, this makes about 5% of the photovoltaic market.
CadTel is 40 times thinner than silicon cells and can be applied directly onto the front glass of the solar panel with vapor transport disposition. These factors significantly change the manufacturing process and reduce the cost of these panels. So they're simpler to manufacture and they're also cheaper to manufacture, which is a bonus.
That sounds like a win on two things.
Yeah, however, we're still learning. We don't know enough about this product yet, and we're still learning about the performance, specifically the voltage deficits. So researchers at the Arizona State University Hallman Research Group, in partnership with the Center for Next Generation Photovoltaics at Colorado State University, the National Renewable Energy Laboratories in Golden, Colorado, and First Solar in Tempe, Arizona, are all working together to understand CadTel and how we can use it to improve solar electricity generation. They're using a measurement technique called external radiative efficiency, or ERE, which helps them gather information. And what they found is that the voltage deficits are not related to interfaces between different materials, which was the common assumption. The issues are actually related to selectivity. Essentially, the electrons within the cell go the wrong way and cancel each other out.
The selectivity issues tell researchers that the semi-permeable membranes are imperfect, which was previously assumed to not be an issue and was overlooked. By doping the absorbers, it can help improve selectivity by only letting the electrons flow one way through the membrane. The external radiative efficiency measurement technique is really the star of the study because it will allow researchers to test many other advanced materials and monitor device degradation in the field, which is all around great.
So what I thought was really interesting about this is we've been building solar panels for a few decades now, and we've been using them all over, and we've kind of just been following a pretty similar model for all of these panels. And I thought it was really interesting that one of the things that they thought wasn't an issue that they completely overlooked is actually the cause of the reduced effectiveness and efficiency of the panels. And so now they have this opportunity to go back and make some adjustments to that portion of the panel. And hopefully we can see some huge gains in efficiency, which is really, really exciting, because the more efficiency we can get out of these panels, the less panels that we need in solar farms, the less manufacturing is required, the lower the cost, and the faster we can get to more sustainable power generation around the world, which is always really, really exciting.
Yeah, and then if the efficiency of the solar panels improves significantly, and like Nicole said, if the footprint itself of the solar panel can be reduced, suddenly it's possible to have viable solar panel installation in cities or in buildings or on top of houses or just in smaller areas than what's typically required now for solar farms that are generally located outside of cities or built up areas. So it makes it accessible to household owners and consumers, which I think is really, really exciting.
Not only based on the area, but also the cost. So when solar panels first started becoming popular, it was like a 40, 50-year payback for you to put them on your house. A lot of people weren't really interested in doing it unless they were really driven by the sustainability factor. But the cheaper you can get it, the smaller the footprint, the more uptake you're going to get on using this product in residentials and other buildings. I think you're also going to see a lot more of this on the roofs of commercial buildings, which will be really great. As well as, and we did this in a mini failure episode, there's a building, the CIS building in Manchester, UK, has photovoltaic panels as the exterior of the building for this one section of the building that doesn't need windows, that had cladding that was poorly installed and was falling off. And so they put on these photovoltaic panels in an effort to correct the cladding or to reclad that section, which I thought was really cool. So, check out our Patreon if you want to hear that episode.
Yeah, so I hope all this technology sees some success, and eventually, over time, we see solar panels that are built from and with this technology. So if you want to read more about the CADTEL study, check out the links on the webpage for this episode at failurology.ca. This week's episode of Failurology is brought to you by the Sit Down Stand Up Paddleboard Company.
Whether you like to sit down or stand up,
the Sit Down Stand Up Paddleboard Company has something for you.
Don't miss our paddle sale. It's quite the ordeal.
Now, on to this week's episode. We're talking about another engineering marvel. In this episode, we're talking about the James Webb Space Telescope.
So if you've been following the show, you'll know that every 10th episode, we take a little bit of a break from engineering failures and we cover an engineering marvel. Because 1, the failures get a little bit heavy, and 2, the marvels are so interesting and we really love talking about them. I do want to say there is a lot of information about the telescope. A lot. There's no way we're going to cover every single thing in this episode. So I'm just going to let you know up front, we're not talking about everything. But we're going to focus on the things that we think are most interesting. And of course, as always, we're going to include an overview of the telescope, its purpose, its mission, and construction, which are usually the things that I find most interesting. So again, we're not going to cover everything. We're going to try and get to all the fun facts about the telescope and give you we hope, a general overview of what the telescope is hoping to accomplish in its lifetime. The James Webb Space Telescope launched on December 25th, 2021, so just this past Christmas, at 12:20 Greenwich Mean Time from the Guyana Space Center, which is a European spaceport located in French Guiana, which is in South America. It entered service in February 2022, and I believe just in the last couple months or couple weeks, all of the solar arrays were fully deployed and the telescope was in full operation. It was designed primarily to conduct infrared astronomy, and it was developed by NASA in collaboration with the European Space Agency and the Canadian Space Agency, which is always exciting. Go Canada. I feel like we have a small representation in the space market, but we do really cool stuff. So, in the International Space Station, we made the Canada arm.
I believe on the International Space Station, I believe that's Canada Arm 2. First Canada Arm was developed for the shuttle program. But either way, Canada has made significant contributions, I think, into spaceflight that probably a lot of people don't know about, but there's some fairly critical pieces that are used on space flights and on shuttle missions that were developed in Canada or by Canadians working for NASA.
The James Webb Space Telescope cost $9.7 billion US dollars. So not a small amount of money, but there are high expectations for this telescope. And I think once we kind of go through that all, that $9.7 billion will hopefully pay for itself one day.
I really hope it does. The Hubble Space Telescope, it's taken some really cool pictures of our galaxy, but it's a little dated right now. It's kind of like using, maybe a pre-digital camera or like a 35 millimeter point and shoot camera. It gets the job done in a very limited range of applications, but it's not quite as good as a new professional SLR digital camera.
Yeah, so like Brian mentioned, the Hubble Space Telescope, we are going to get into this in quite a bit more detail, specifically some of the differences between the two. But the James Webb Telescope was ultimately created and built to replace the Hubble telescope because it is quite outdated in its abilities. And so this new telescope is meant to take its place and, take us for the next few decades into the future until the technological revolution advances further and further and we need another new telescope. One of the other things that I think is really cool about this project, several thousand scientists, engineers, and technicians across 15 countries all work together to build, test, and integrate this telescope. There was also 258 companies, government agencies, and academic institutions that participated in the pre-launch project. I think that's pretty cool that you're bringing together all of these people, thousands of people, hundreds of companies, multiple countries are coming together to all work on a common goal and this common project. And I think that's really good for the future of science. Seeing all these people work together for a common goal is really great. The world is messy and we don't always get along. And so to see us all come together, just makes my little physics heart sing. You're wondering, how did it get its name? James E. Webb was the administrator of NASA from 1961 to 1968 during the Mercury, Gemini, and many Apollo programs, and they've named the telescope after him.
I think that's quite a fitting name for somebody that spent a long time administering some of our earliest space programs. Mercury was the first program that sought to put American astronauts into space, and then through Gemini and through the Apollo program, which eventually landed American astronauts on the moon.
So speaking of the name, Scientific American, which is a magazine, released an article in March of 2021, which urged NASA to reconsider the name based on Webb's alleged complicity during the Lavender Scare persecution of LGBTQ employees during the Harry Truman administration. For those like myself, I wasn't around at that time. I hadn't heard of the Lavender Scare before. But from what I've read, gay men and women were said to be a national security risk, and communist sympathizers led to a call to remove them from state employment, which is extremely unfortunate. And I really just wish these people didn't have to go through that experience. It's ridiculous and unnecessary. That said, NASA declined to rename the telescope, and their claim was that there's no evidence Webb participated in the Lavender Scare. And honestly, I wasn't there. I don't know. I have to assume the claim to change the name wasn't baseless and that NASA did their research. But as we know from other episodes we've done, NASA also does make some questionable decisions when it comes to crew safety, for one. And so I don't know. I don't know if he was involved or not. I don't know if NASA did their due diligence when they picked the name. I don't know all of that, but I do think that was an interesting part of the telescope and its history. And so I didn't want to gloss over that. I did want to touch on that. And so that was definitely a controversial thing that happened when they released the name of the telescope.
Development of the James Webb Space Telescope first began in 1996 with a planned launch date of 2007. When we're recording this episode, it is 2022. So they have missed their planned launch date by a couple years.
Like 14 years. They missed it by 14 years. That's like a whole adult person. Almost. That's an almost adult person. In Alberta, you can drive when you're 14.
You have to have somebody sitting beside you. You have your learner's permit. But yeah, somebody could drive at 14. This telescope missed the launch window by the same amount of time that it takes for somebody to be able to drive and operate a motor vehicle under supervision in the province of Alberta. However, the telescope, it did undergo a major redesign in 2005. There were a whole host of delays and cost overruns throughout the design and construction, such as a ripped sunshield during practice deployment. There was an independent service board recommendation. There was threats from the US Congress to cancel the project, problems with the rocket and the telescope itself, communication glitches between the telescope and the launch vehicle, and of course, COVID.
Oh, COVID. Good old COVID.
So construction of the telescope was completed in 2016, and they followed that up with 5 years of extensive testing, which is a good thing if you're going to launch something into space and never touch it again.
So I will say, I don't know a ton about the different space projects that NASA has undertaken, or even some of the other organizations. Brian is definitely much more up on that than I am. But I will say, we've done 2 episodes on NASA projects. We've done Apollo 1 and the Challenger space shuttle. And I will say a 14-year delay is extensive, and they don't all get delayed that much, but things going wrong and the project's almost not happening and then happening and almost not happening again, and redesigning and testing not going well. This is all par for the course. So a delay is not surprising.
Yeah, and this is a fairly monumental, actually it is a monumental project that NASA and other space agencies have undertaken. It's not like you can just go to the telescope store and grab a James Webb Space Telescope off the shelf.
Well, don't they have a Lego version?
No, actually they don't have a Lego version yet, because if they did, I would have it. It's in the idea stage right now. Hopefully it gets funded. There's a bunch of cool space Lego, so this will be part of my space Lego collection if they ever make a model of it. But as I was saying, I do think extensive testing in programs like this is a really good thing to have. You need everything to work perfectly on these telescope systems for when they launch, when they deploy, when they collect data, when the satellite downlink happens for the data that you've collected. If anything goes wrong in space, especially with the James Webb Space Telescope, there's essentially no ability to fix it. Something incredibly minor going wrong could cost you the entire space telescope, and then you would get no data, or no data from the telescope, and it essentially waste almost $10 billion. Hubble did have some early struggles, but with a couple spacewalks, they were able to rectify the issues that did crop up with Hubble.
Like we've talked about on a lot of the plane episodes specifically, but also applies here. If there's a problem with this telescope, you can't just pull over to the side of the road and fix it. You're up in space. You're on your own up there. And the telescope itself is unmanned. So you want to be absolutely sure that it's going to work before you send it up there. Otherwise, you're just throwing $10 billion down the toilet.
That's a lot of money for something expensive. Something that just essentially becomes space debris at that point. Junk in space. And there's already enough of that up there. So the prime contractor for the James Webb Space Telescope was Northrop Grumman Aerospace Systems. If anyone's familiar with I guess, early aviation or Cold War aviation and spacecraft design, so the Grumman part of the name was a company that built the Apollo lunar module, as well as the Grumman LLV, which is the mail truck, the very tiny mail truck that everyone sees driving around in residential communities. So this is a company that developed, the lunar module and mail trucks. Northrop Grumman Aerospace Systems developed and built the spacecraft element, including the satellite bus, the sunshield, the deployable tower assembly connecting the optical telescope element to the spacecraft bus, and the mid-boom assembly which deploys the large sunshield. So they built a lot of things on this telescope, a lot of really critical things that make this a telescope. In addition to Northrop Grumman Aerospace, Ball Aerospace and Technologies developed and built the optical telescope element itself and the integrated science instrument module. So as we previously mentioned, the James Webb Space Telescope was intended to succeed the Hubble Space Telescope, which is currently up in space. And the Hubble Space Telescope was launched in 1990. It still remains in operation today. The James Webb Space Telescope will be the largest, most powerful space telescope ever built. So it'll allow scientists to look at what our universe was like about 200 million years after the Big Bang. Like, that's a super long time to be able to look back into the universe. Like we mentioned previously, the Hubble telescope was great for its time, but now we need a stronger, better telescope, one that can view objects too old and distant, or sometimes up to 100 times fainter than what the Hubble Space Telescope can currently view.
How big is the James Webb Space Telescope? Because I'm imagining the telescope you'd buy at the telescope store, but it's probably much bigger than that.
It is significantly bigger than that. The sunshield piece on the James Webb Space Telescope, it's 21.2 meters by 14.2 meters, which I believe is about the size of a tennis court. And the whole telescope assembly, it's 8 meters tall, or the equivalent height of a 3-story building, I think. So this is not a tiny telescope that you get at the telescope store, like Nicole said. Like, this telescope is the size of a small apartment building is. With the James Webb Space Telescope, scientists are hoping to enable a broad range of investigations in astronomy and cosmology, hopefully viewing the first stars or formations of the first galaxies, which is really cool. Part of the issue, though, if we find some of these galaxies that are really far away, light speed travel is something that we're going to have to perfect just to reach these places. So even if we find some of these places, it might take us a long time to develop the technology to get to those places.
Or at least to get to those places in the span where the people who get on board are still alive when they make it there. Because it may take 3 generations worth of time to get to that new planet that they find.
And that's traveling at light speed, so it will take quite a while.
Should we explain light speed? Because I feel like it takes a hot minute to get your brain around it.
Like, light years are the distance that light travels in a year.
How many kilometers is a light year?
So it's approximately 6 trillion miles.
Per year?
Yes, 9.7 trillion kilometers. So if something's 100 light years away, 970 trillion kilometers away.
Yeah, that's a little bit farther than my brain can really comprehend. I struggle to even comprehend the size of the globe. Like I follow the math and how many kilometers it is in circumference. It's just that my brain can't visualize the planet as a whole. And so it's a lot. But 9.7 trillion kilometers, I mean, that's a lot of kilometers.
The primary mirror on the James Webb Space Telescope, which is called the Optical Telescope Element, or the OTE, is made up of 18 hexagonal mirror sections, and together these make up the 6.5 meter diameter mirror. So for comparison, the Hubble Space Telescope, which is currently the best telescope that we have in space, it has a 2.5 meter diameter mirror. So mirror segments on the James Webb Space Telescope are made up of gold-plated beryllium, and the gold plating provides infrared reflectivity and durability. And in total, there were 48 grams of gold that were used in the telescope's construction. The gold plating on the mirror, it is incredibly thin. It is 100 nanometers thick, and gold was used since it's highly reflective at infrared wavelengths. So as I mentioned, the optical telescope element on the James Webb Space Telescope, it has a diameter almost 3 times that of Hubble, which gives the James Webb Space Telescope a light collecting area about 6.25 times that of Hubble. So significant gains in the amount of light that this telescope can collect, which is one of the reasons that it can see so much further into the galaxy compared to Hubble. So the Hubble Space Telescope, it uses ultraviolet, visible, and near-infrared spectrums, while the James Webb Space Telescope uses long wavelength visible light through the mid-infrared band. Interestingly, I think, the James Webb Space Telescope has to be kept below 50 degrees Kelvin or minus 223 degrees Celsius in order to observe faint signals without interference from other sources of warmth. It's a good thing it's in space, because fortunate for humans and unfortunate for the James Webb Space Telescope, it's not that cold on Earth. So this would not work very well for observing things on Earth. There'd be too much infrared and interference, too much heat on Earth. And the telescope itself, it operates at 15 degrees Celsius, which radiates strongly in the infrared band. So the telescope needs to be shielded a lot on this. So the orbit of the James Webb Space Telescope is around the Sun, and it orbits at about 550 kilometers from the Earth's surface. And the orbit is such that it keeps out of the Earth's shadow and the Moon's shadow, which is important if you're trying to observe stuff in space. As I mentioned, it has a sunshield on it. So the sunshield is a 5-layer kite-shaped sunshield, and it protects it from warming by the sun, moon, and the earth, which are all incredibly critical for observing in the frequency ranges that the James Webb Space Telescope is looking to observe in.
So the telescope has a lot of really interesting features. We're going to get to my favorite. I'll save that one for last, but there's a bunch of them. So the telescope design emphasis, as Brian mentioned, is from the near to mid-infrared, and that's for 3 main reasons. The high redshift, which is very old and distant objects, have visible emissions in the infrared band, meaning that they can only be observed with infrared astronomy. Colder objects, such as debris and planets, emit most strongly in this infrared band. And this band has been too difficult to study from on Earth or with the Hubble, and so thankfully the James Webb Space Telescope is here to give us some more information on this band. Telescopes on Earth have to look through the Earth's atmosphere, which is very opaque in many of the infrared bands, and even where it's transparent and they can see through it, there's many other chemical compounds such as water, carbon dioxide, or methane that exist that just tarnish what those telescopes are able to see. And so having this telescope out in space gets rid of that obstruction completely. The James Webb Space Telescope can also view nearby objects and opportunistic and unplanned targets within 48 hours of a decision to do so. So yes, the telescope is in space, and yes, it's unmanned, but they still have the ability to turn it and rotate it and move it around so that it can see other things, and they just need 48 hours notice. That seems like a lot of notice, but I think in terms of things you're viewing in space, that's pretty fast. And it can downlink 57.2 gigabytes of recorded data every day with a maximum data rate of 28 megabits per second. As I said, I'm saving the best for last. Out of all the things on the telescope, you know, it's a fantastic telescope with mirror array, and it's put up to space on a rocket. The part that I think is the coolest is the sunshield. The sunshield blocks light and heat from the sun, earth, and moon, and its position keeps the sunshield between those objects in the telescope at all times. So the telescope is always on the cold side from wherever that heat source or light source is. The sunshield has 5 layers, and each of them are as thin as a human hair, which is in itself fascinating. And it's made from Captain E, which is a material I'm not familiar with. It's a polyimide film with aluminum-coated membranes and a layer of doped silicone on the sun-facing side of the 2 hottest layers, which helps to reflect the heat. As we had mentioned earlier on in the episode, there were accidental tears in what has to be a very delicate film structure. I mean, each of the 5 layers are as thin as a human hair. Imagine with all of them together, it's still very, very thin. And that ripped during testing in 2018, which ultimately delayed the project. The sunshield was hand-assembled and designed to fold 12 times to fit in the rocket's payload. And it blocks about 60% of the sky from one position. But because it rotates and moves around, this telescope can still see all of the sky over a 6-month period. The sunshield is also helped by a cryocooler to make sure that the infrared instrument stays in its optimal supercool temperature.
So as we mentioned, the telescope's primary mirror is made up of 18 hexagonal segments. So they're kind of assembled like honeycomb to make the primary mirror. As Nicole mentioned, with the sunshield, all of this needed to fit in a rocket payload bay, which is not exactly massive. It was impossible to construct the mirror for the James Webb Space Telescope as a single element. To position all of the 18 hexagonal mirror segments on the James Webb Space Telescope, there are 132 small motors or actuators that position and occasionally adjust the optics to combat environmental disturbances.
And this, my friend, is my second favorite part. 132 motors and actuators is super cool. You can basically control all of the little individual mirrors to aim everything. You can't see me right now, but I'm making robot moves with my hands right now because I'm pretending that I'm the mirrors. It's so cool. So cool. So interesting.
And to me, when they were doing the deployment of the James Webb Space Telescope, this was one of the areas where if something was going to go wrong and ruin the entire project, this could be like if one of those actuators for the mirrors didn't work, it would compromise the integrity of the entire collection mirror, and it could impact data that was being collected. So there was a lot of potential for things to go wrong with these tiny actuators. So as I mentioned, there's 18 individual mirror panels. There's 7 actuators on each mirror, and then 6 on the central one. So 18 times 7 plus 6 is 132 actuators. So these actuators, this is mind-blowing to me. The actuators can position the mirror within 10 millionths of a millimeter in accuracy. That's a ridiculously small amount that the actuators can move the mirror. I'm just astounded by how accurate these things are.
Well, and it's funny because, in HVAC and plumbing design, it's a dialed in science for sure, but there's ranges. So, a 4-inch pipe doesn't have a specific flow rate. It has a range of flow, a minimum and a maximum that pipe is effectively used for. And I like to joke when people get really, really complicated and try to dial things in to the millimeter or to, decimal places. I like to joke, we're not building a rocket ship, because in my line of work, of course, there are scenarios where, you're measuring in quarter inches or half inches, but at no point are we down to even millimeters of accuracy is a stretch for the most part. But 10 millionths of a millimeter is an insane level of accuracy.
Are you going to adjust your saying and say, hey, we're not trying to reposition a space telescope mirror?
I could, but I don't know if that joke will land as well.
Probably not.
Maybe I'll test it out though. I'll crowd work that.
Let us know how that one goes. The optical design is referred to as a 3-mirror anastigmat. This is similar to a satellite dish. There's a large primary mirror that collects information and reflects it to the secondary mirror that sits in front of it, which then dials that back to a third mirror, either in front of or slightly behind the primary mirror. The secondary mirror on the James Webb Space Telescope, a little bit smaller, it's 0.74 meters diameter, and this has a fine steering motor as well.
The Integrated Science Instrument module holds 4 science instruments and a guided camera. It has a near-infrared camera, a near-infrared spectrograph, a mid-infrared instrument, and a fine guidance sensor and near-infrared imager, as well as a slitless spectrograph. The spacecraft bus hosts computing, communications, electric power, propulsion, and structural parts. And that bus weighs 350 kilograms and supports the 6,200 kilogram telescope. So this thing is not light. The spacecraft bus, which is kind of the brain of this thing, it's made of graphite composite material.
There were 4 goals of the James Webb Space Telescope program. 1. Search for light from the first stars and galaxies that formed in the universe after the Big Bang. 2. Study galaxy formation and evolution. 3. Understand star formation and planet formation. And last but not least, study planetary systems and the origins of life.
So as we mentioned at the beginning of the episode, there is a lot of information on this telescope, and there is no way we're going to cover it all. So we focused this episode on the things that we thought were most interesting, which, as you can see for me, that's the telescope itself, the different mirrors and arrays, and then the sun shield. The sun shield is super cool. It's 5 layers of super, super thin material that folds 12 times and then comes out into this big shield and protects the telescope and keeps all of the equipment cool. So those are the parts that we thought were the most interesting. Those are, I think, the key components on the engineering side of how this telescope was designed and built. But there are hundreds, if not thousands, of articles on this telescope, and I encourage you to go out and look up more information if you want to read about it. We just wanted to plant the seed on this telescope and hopefully inspire you guys to go out and do more reading on this telescope. And if you find something really, really cool about it, email it to us. We love hearing from you guys.
So when we're recording this episode, so we record the episodes a couple weeks before they come out, the James Webb Space Telescope has sent back some test pictures, test images in the infrared band, as part of this testing cycle. And these are the sharpest images that have ever been seen of the galaxy. It is phenomenal, the level of detail that's available from this telescope, even in the testing phase. It's kind of like having an old 13-inch standard definition TV, and then you upgrade to a giant 75-inch 4K, TV. You're still watching the same thing. You're, the same sports or the same show, but suddenly everything's much more clear. So there you have it, a telescope 26 years in the making. The James Webb Space Telescope is a promising addition to our efforts of space exploration in the fields of astronomy and cosmology.
For photos, sources, and an episode summary from this week's episode, head to failureology.ca. If you're enjoying what you're hearing, please rate, review, and subscribe to Failureology so more people can find us. If you want to chat with us, our Twitter handle is @Failureology. You can email us at thefailureologypodcast@gmail.com. You can connect with us on LinkedIn, or you can message us in the Patreon app. Check out the show notes for links to all of these. Thanks everyone for listening, and tune into the next episode where we'll talk about the Teton Dam, a completely preventable dam failure that decimated many towns downstream. But more on that next time. Bye everyone. Talk soon.